next problem is called subsets. We are given an array of nums of unique elements. Important unique. Return all possible subset, the power set. The solution set must not contain duplicate subsets, and we have to return the solution in any order. Now, for example, for the example with only one number of 2, we can basically have the number 0 or an empty set. So we can basically choose the number 0 to be present in a set or for it to not be present in a set. The first example is basically the same. And there's an option to choose none of the elements, which is just an empty set. There's an option to choose only one single element from the input array. Then we can have all pairs. And the last option is to choose all of the elements inside the array. The funny thing to notice here is that the number of subsets, the power set length, will be 8. And we can there's similarity between the subsets, the power set, and the binary representation, the configuration of the number. So, for example, for 3 digits, for 3 numbers, we can use a binary number of length 3 to determine if any of the element is present. So, for example, if we want to reflect that all all elements are present, we will use 1, 1, and 1. For example, if the first element is not present, we will set the first bit to 0 and the rest of it to 1. Same goes if none of them are present, we'll just have 0 and 0. And if you think about it, to represent these 8 numbers from 0 to 7, you have 8 numbers. You can only have 1 or 0, so you have 2 options. And to get 8, you basically need a length of 3. So 2 to the length of the string that you need. So basically that's our time complexity for the subsets. Because if you have a string of or a sequence of numbers which is equal to n, we will have 2 to the n computation to generate all of the subsets. Now for the constraints, the length of the array is from 1 to 10, and the numbers that we have inside the array from -10 to 10, nothing important, and all the numbers of nums are unique. So we don't have to worry about having the duplicates in the final output. Now if you go to an example, let's say we have the same example, 1, 2, 3. We have 2 options. So we know that we have 2 options. Now the base case is that we run over all the candidates. So the things that we'll be passing to our helper function, which we always have for the backtracking problems, is the index. It will be the set of candidates, so input array. And we will have the current list, which is our list that we are generating, and also the result that we will be adding this current list to once we hit the base case. So once the index is outside the boundary of the input array, we are out of the candidate, so we can add that current list to our final result list. Now we have 2 options, and the options is either to choose the element or not. So for now, we can either choose it, and I will just declare this little rectangle with X that means that we haven't chosen it. And this will be our index 0, so we will just increase the index so we can go to the next candidate, and we recursively call the helper function, so we can go down the recursion tree. Now for the next element, we can either, again, choose number 2 or don't choose it. We will again move the index, and as we are doing this, we are putting the options that we choose inside our list of digits. So we will choose 1, we will choose 2, and then we will choose 3, or we will not choose 3. So there are 2 options. Let's just go to the left subtree first. So we have chosen this one, and we will call the index will increase, and we will call again the helper function. But now we hit the base case, and we can add this list to our result list. Now when we go back to the number 2, and we will pop the last element from our list that we are generating, so it will be 3, and we will go to the right subtree. And because we don't have to add anything, we will just propagate to next level, but that index will be equal, it will be out of the boundary of the size of the array. So this sequence of elements will be added to the final list. And that's how we will go through each of them. We will go back, we will first choose the options that we will choose the element, and then we will go to the right node, which basically means that we are not choosing the element. Each time we have two options, and the depth of the tree is n, so it will be 2 to the power of n times the multiplication. Because we are adding the array, we are creating the new array from the value that we are using to generate the subset, the new subset. We will have a multiplication of n, which n is basically the number, the length of the initial array. And for the space, because we only have this current list, the space will be, again, the only thing that we are propagating back down to the recursion tree is the array, and this array, which can be at most n. So the space complexity will be linear to the length of the initial array. First, we will declare our result, which is list of list, which will present our power set. We'll be adding the sets that we are generating inside our helper function inside this result, and at the end we will return it. Our helper function will, as always, take the index, so we can know where we at the set of candidates, which brings us over to the next parameter, which is the initial array, which presents the list of candidates that we can choose from. The current list is basically the set that we are currently generating inside the helper function, and the result is the list of all sets, the power set, that will be returning as the final output of the function. Next, if we get to the base case, in which basically means that our index is out of boundary of the set of candidates, we run out of the candidates. We will be just adding the current list, which is our set that we have generated traversing through the recursion tree. We will go back in the recursion tree, and in the regular scenario, we will first add to the set that we are generating the current element, the current candidate at the that index is pointing to, and we will iterate. We will go a level down in the recursion tree by incrementing the index. But on this is the option of selecting the element. The option of not selecting the element is to remove the current element and just move to the basically the right node in our diagram. We will move without adding the current candidate.